Since ancient times, humanity's yearning for the brilliant starry sky above has been deeply etched into the very DNA of our civilization, like an indelible brand. From the halls where gods resided in ancient myths to the vast territories where starships traverse in science fiction, interstellar travel has always been our most magnificent and soul-stirring dream. This desire, which spans across time and space, is not merely simple curiosity, it carries our drive to explore the unknown, our infinite imagination regarding extraterrestrial life, and the ultimate vision of seeking broader living space, acquiring precious resources from the deep cosmos, and pushing our civilization continuously forward. For ages, we have lived and thrived on this blue planet, Earth, but there will come a day when finite resources and growing demands force us to turn our gaze toward more distant horizons. Interstellar travel is not just a leap in science, but an expansion of civilization itself. It will fundamentally alter our understanding of our place in the universe and may even redefine the very concept of humanity. Embarking on an interstellar journey means we will face the immense challenges posed by the vastness of the cosmos, including daunting distances, unimaginable time scales, and extremely harsh environments. The story is long, so let us speak of it as if in a dream, but before we begin, remember to like and share. The vast void is filled with lethal radiation, and tiny debris could strike a spacecraft at high speeds, while the prolonged voyage tests the very limits of human physiology. Yet, these challenges also harbor unprecedented opportunities. Every technological breakthrough, whether the birth of a new propulsion system or the innovation of life support technology, could herald another leap for human civilization. These breakthroughs do not only serve interstellar exploration, their spillover effects will also profoundly impact our lives on Earth. This discussion will combine the latest scientific progress to systematically introduce the current and future pathways of interstellar flight and the challenges they face, looking forward to a future where humanity walks toward the sea of stars. We will explore the evolution from classical rockets to disruptive propulsion technologies, analyze the physiological and psychological difficulties of crewed interstellar travel and their potential solutions, and look toward the cosmic resources and potentially habitable worlds waiting to be discovered. Ultimately, we will reflect on how this grand exploration will shape the future of human civilization and how we might truly realize this eternal interstellar dream. The scale of the universe is far beyond the imagination of our daily lives, manifesting its grandeur in an awe-inspiring way. Within the solar system, we usually measure distance in astronomical units. 1 astronomical unit is the average distance from the Earth to the Sun, approximately 149,600,000 kilometers. This unit is very convenient for describing distances between planets. For instance, Mars is only 0.38 astronomical units away at its closest, while Jupiter is around 5.2. However, when we look beyond the solar system, this unit becomes insignificant. Thus, astronomers introduced the light year, which represents the distance light travels in a vacuum in 1 year. This is an incredible length, roughly 9,460,000,000,000 kilometers. The light year is the fundamental unit used to measure galactic scales, intuitively telling us that even at the fastest speed in the universe, the speed of light, it takes a long time to reach distant stars. Another commonly used unit is the parsec, which is based on the parallax of stars to calculate distance. 1 parsec is approximately 3.26 light years. This unit is more common in professional astronomical research because it is directly related to the stellar parallax angle, making calculations easier. Take Proxima Centauri, the closest star system to us, as an example. It is about 4.2 light-years from Earth. This means even traveling at the speed of light, it would take more than 4 years to arrive. Our Milky Way galaxy has a diameter of about 100,000 light-years and a thickness of about 1,000 light-years. This means that even long-distance travel within our own galaxy is comparable to crossing a giant cosmic island. Even more shocking is that the observable universe is still expanding, and more distant galaxies are moving away from us at staggering speeds, possibly even exceeding the speed of light. This undoubtedly reveals the ultimate challenge of interstellar flight: how to bridge these desperately vast distances. These numbers clearly demonstrate the boundless nature of the universe and explain why simply reaching the nearest star remains a massive challenge for current human technology. It requires us to rethink the concepts of time and space. Traditional chemical rockets, though they sent humans to the moon and explored many planets within the solar system, expose their limitations when faced with the grand goals of interstellar travel. The Hohmann transfer orbit, which we often mention, is the most fuel-efficient design, but it is relatively slow and takes an extremely long time to reach a target. This type of orbit utilizes planetary gravity assists, but its essence remains based on the principles of classical physics, Kepler's laws, and Newtonian mechanics, generating thrust by burning fuel. The acceleration capability of a rocket has an inherent limit known as the rocket equation. This equation shows that the final speed a rocket can reach depends primarily on its exhaust velocity and the mass ratio, that is, the ratio of the rocket's total mass at liftoff to its final payload mass. To obtain higher speeds, we need to carry more fuel, but more fuel means a heavier rocket, which in turn requires even more fuel to move, creating a vicious cycle that makes it difficult for rockets to reach speeds sufficient for interstellar travel. This inherent inefficiency limits the final velocity and the payload capacity. For example, accelerating a 1 kilogram payload to 1% of the speed of light might require millions of tons of fuel, which is unimaginable in engineering. More importantly, after enduring the long journey to the destination, additional fuel is needed to decelerate so the craft can be captured by the target planet's gravity or land safely. This further increases fuel consumption, making the fuel requirement for a single mission astronomical. This means even traveling to the farthest planets in the solar system, like Neptune or Pluto, would take decades or longer. Using the most famous deep space probes, Voyager and Pioneer, as examples, they are the farthest man-made objects in history, yet they took decades just to reach the edge of the solar system. To completely leave the solar system and head toward the nearest star would take tens of thousands of years. This fully illustrates the helplessness of traditional chemical rockets on an interstellar scale. They are better suited for exploration within the solar system rather than serving as a vehicle for crossing light years. Their speed limitations prevent them from satisfying the human desire for rapid interstellar travel. Under the extreme conditions of approaching the speed of light, Einstein's special relativity reveals a stunning phenomenon: time dilation. According to special relativity, when an object moves at a speed close to the speed of light, its passage of time becomes slower compared to a stationary object. This means for astronauts conducting high-speed interstellar travel, the time they experience on the ship will be much shorter than the time experienced by people remaining on Earth. For example, an astronaut traveling at nearly the speed of light might feel only a day has passed while crossing 10 light-years, whereas over a decade would have passed for those on Earth. This difference in time is a real physical phenomenon that can be precisely described through the Lorentz transformation. The famous twin paradox vividly explains the ethical and practical problems brought by this time dilation. Consider a pair of twins. One goes on a high-speed interstellar journey, and when he returns to Earth, he finds his brother has grown old and gray, or perhaps even passed away, while he himself has hardly aged. This massive discrepancy in time will pose unprecedented challenges to the family and social relationships of interstellar travelers. It could lead to separation from loved ones and a total disconnection from one's own era. Furthermore, communication between astronauts on a long journey and Earth will face massive time delays. Even transmitting signals at the speed of light, a message from Proxima Centauri would take over 4 years to reach Earth, making real-time interaction impossible. However, special relativity also clearly states that any object with rest mass cannot reach or exceed the speed of light. The light speed barrier is an insurmountable limit set by the universe because it would require infinite energy to accelerate a massive object to the speed of light. As an object's speed increases, its mass also increases, thereby requiring even more energy for further acceleration, forming an infinite loop. This means that warp drives or faster-than-light travel, common in science fiction, remain merely beautiful ideas within the current scientific framework, lacking conclusive scientific evidence. Warp drive theory suggests bypassing the light speed limit by warping the space-time around the ship, so the ship itself does not move faster than light but the bubble does. However, this requires negative energy or exotic matter, which has not yet been discovered in nature. Wormholes are possible space-time shortcuts that could theoretically connect distant points for instantaneous travel, but this also requires extreme conditions, such as the interior of a black hole, and their stability and controllability remain unknown. Breaking the light speed barrier would require a revolutionary breakthrough in physics or the discovery of cosmic laws we do not yet understand. This is not just an engineering puzzle, but a challenge to the very foundations of modern physics. Therefore, for the foreseeable future, human interstellar travel must still face the long journeys and time dilation effects brought by the light speed limit, making every interstellar mission an ultimate test of human patience, wisdom, and perseverance. Faced with these challenges, scientists have not stopped at the limits of chemical rockets. Instead, they are actively exploring various disruptive propulsion technologies to break through the constraints of speed and distance. Nuclear propulsion is considered an important direction for the next generation of power. It can provide energy densities far exceeding chemical fuels. The most direct implementation is the nuclear thermal rocket. This thruster uses the immense heat generated by a nuclear reactor to heat a propellant, usually liquid hydrogen. The hydrogen, heated to extreme temperatures, expands rapidly and is exhausted through a nozzle at high velocity, generating powerful thrust. The advantage of this method lies in its high specific impulse. Specific impulse is a key metric for measuring rocket engine efficiency. It means that for the same mass of fuel consumed, a nuclear thermal rocket can produce a much larger total impulse, allowing the ship to reach higher speeds. Although challenges remain in nuclear safety and material temperature resistance as materials must be developed to withstand extreme heat and radiation, NASA's nuclear engine programs in the last century conducted extensive research and ground testing, demonstrating great potential. In recent years, with progress in materials science and nuclear technology, nuclear thermal rockets have gained renewed attention and investment. They are seen as a key step toward rapid travel within the solar system and preliminary interstellar probes. Their development will significantly shorten travel time to Mars or other outer planets, providing more reliable power for crewed deep space missions. Another form of nuclear power is the nuclear electric rocket, which takes a different path of energy conversion. It first generates electricity through a nuclear reactor and then uses that power to drive ion or Hall thrusters. These work by using electric or magnetic fields to accelerate ionized gases, such as xenon, exhausting them at extremely high speeds to produce thrust. Although the thrust of ion and Hall thrusters is relatively small, usually only on the level of newtons, far below the powerful instantaneous thrust of a chemical rocket, their specific impulse is extremely high, and they can operate continuously for years or even decades. This means they can provide a weak but constant thrust over a long period, eventually allowing the spacecraft to reach very high velocities. This characteristic makes them ideal for deep space missions requiring long-term acceleration. For example, Japan's Hayabusa probe successfully used ion thrusters to travel to an asteroid and return samples, and NASA's Dawn probe utilized them to explore two large objects in the asteroid belt. In the future, nuclear electric rockets are expected to carry larger payloads to even more distant targets. Even more promising, yet most challenging, is the nuclear fusion rocket. This would use the vast energy of controlled nuclear fusion reactions to propel a ship. If miniaturized and efficient fusion reactors can be achieved, they would provide unprecedented energy density, theoretically allowing ships to reach speeds approaching a significant fraction of the speed of light, completely transforming interstellar travel. The plasma generated by fusion reactions could be used directly as a propellant, or its heat could drive other mediums. However, fusion technology itself is still in the research stage. How to initiate and sustain a fusion reaction and how to safely and effectively convert fusion energy into thrust remain massive scientific and engineering hurdles that may take decades or even centuries to overcome. Beyond nuclear power, laser or light sail propulsion are also highly anticipated technologies. They cleverly utilize the energy of photons to drive a ship, avoiding the burden of carrying massive amounts of fuel. The simplest concept is the solar sail, which uses the radiation pressure of solar photons to provide thrust. Solar sails are usually supported by extremely thin and highly reflective materials, such as polyamide films. When solar photons strike the sail, they produce a tiny amount of thrust. Although the thrust from a single photon is negligible, with a large enough reflective area and long exposure to sunlight, a solar sail can continuously gain speed over time. The advantage of this technology is that it requires no fuel. As long as there is starlight, it can continue to accelerate, enabling extremely long-range voyages. However, its limitations are also obvious. The thrust is very small, acceleration is slow, and the effect weakens rapidly as the ship moves away from the star, making it unsuitable for quickly reaching distant targets. Japan's Ikaros probe in 2010 successfully verified the feasibility of solar sail technology in space, and NASA's light sail program is also actively progressing, providing a new power option for future deep space probes. A further vision is the laser sail or photon rocket. This concept involves a giant laser array on Earth or in orbit firing high-energy laser beams at a huge light sail on a lightweight spacecraft to push it forward. The core idea is to leave the massive energy source, the powerful laser transmitter, on Earth or within the solar system, while the spacecraft itself can be made extremely light, carrying only necessary sensors and communication systems. The most famous of these is the Breakthrough Starshot initiative, which aims to launch miniature probes and use a powerful ground-based laser array to accelerate them to 20% of the speed of light in a very short time, thereby reaching Proxima Centauri, 4.2 light-years away, in just 20 years. The challenges of this technology are immense. First, a laser array of sufficient power must be built, possibly reaching gigawatt levels. Second, light sail materials must be designed to withstand the immense laser energy and reflect it effectively. These materials must be incredibly thin, light, and strong, while enduring extreme temperatures. Furthermore, maintaining the precise aim of the laser beam over such a vast distance and ensuring the probe can communicate back to Earth are unprecedented engineering problems. Nevertheless, laser sails are considered one of the most likely technical pathways to achieve interstellar flight within a few decades, providing a feasible roadmap for exploring other star systems. At deeper theoretical levels, scientists are also exploring the possibilities of antimatter propulsion and various field effect propulsion systems. Antimatter annihilation is one of the most powerful energy conversion methods in the universe. When matter and antimatter meet, their mass is completely converted into energy, following Einstein's mass-energy equivalence equation. If the gamma rays or charged particles produced by antimatter annihilation could be used as a propellant, it would theoretically achieve the highest energy density and efficiency, allowing ship speeds very close to the speed of light. The energy conversion efficiency of this method far exceeds nuclear fission or fusion, with nearly 100% of the mass converted into energy. This is undoubtedly the ultimate energy temptation for interstellar travel. However, the production of antimatter is extremely expensive and consumes vast amounts of energy. Currently, laboratories like CERN can only produce minute amounts of antimatter at staggering costs. How to produce, store, and safely control antimatter in large quantities remains an insurmountable technical chasm. Storage is particularly difficult because antimatter must be completely isolated from ordinary matter, usually requiring powerful electromagnetic fields to suspend it in a vacuum chamber. Any contact with the container walls would result in annihilation. Furthermore, the gamma radiation produced by annihilation requires extreme shielding for the spacecraft. As for field effect propulsion, we touch the boundary between science fiction and reality. These theories often attempt to achieve faster than light travel by manipulating the structure of space-time itself. The warp drive, such as the metric proposed by physicist Miguel Alcubierre, theoretically suggests bypassing the light speed limit by warping the space-time around the ship, contracting it in front and expanding it behind so that the ship moves relative to external space without actually exceeding the speed of light locally. This theory cleverly avoids the constraints of special relativity and sounds very attractive. However, realizing a warp drive requires negative energy or exotic matter, which have not yet been found in nature. These substances would have anti-gravity effects that could cause space-time curvature. Even if they exist, how to generate and control such massive amounts of negative energy is an unimaginable challenge. Wormholes are another possibility, described as tunnels in the universe that could connect distant points in space-time, reducing travel time to zero. But this also requires extreme conditions, such as the interior of a black hole, and their stability and controllability are unknown. Currently, wormholes remain merely a mathematical solution to general relativity equations under specific conditions. Their actual existence and whether they can be artificially created or traversed remain a giant question mark. Some sensational concepts, like the fuel-free electromagnetic drive or M-drive, which claim to generate thrust without propellant, have been generally dismissed by the mainstream scientific community as measurement errors or systemic noise. This is because such concepts seem to violate Newton's third law, the principle of action and reaction. While these ideas are filled with imagination and inspire a passion for exploration, they currently remain in the theoretical or even science fiction realm, far from engineering realization. Their actualization would require a fundamental breakthrough in basic physics rather than simple engineering improvements. Crude interstellar travel is not only a severe test of technology but also the ultimate challenge to the physical and psychological limits of the human body. In the deep cosmos, radiation is the invisible killer. Two main types exist: galactic cosmic rays and solar energetic particles. Cosmic rays originate from extreme astrophysical events outside our solar system, such as supernovae. They consist of high-energy protons and heavy ions that are nearly impossible to block completely. Solar particles, while lower in energy, are numerous and can cause acute damage during solar flares. These particles cause severe harm to the human body, including DNA damage that significantly increases cancer risks and irreversible damage to the central nervous system, affecting cognition and motor function. To counter this, scientists are researching passive protection using heavy materials like water or polyethylene, though their mass increases launch costs significantly. Active protection, such as using magnetic fields to deflect particles, is complex and energy-intensive. We are also looking into anti-radiation drugs and gene repair technologies to increase human resistance. Beyond radiation, microgravity has profound effects. In the long journey, astronauts live in weightlessness, leading to a slow but continuous degradation of bodily functions evolved over millions of years on Earth. The most notable effects include bone loss, where density drops sharply, making bones as fragile as those of an elderly person with osteoporosis. Muscle atrophy is also unavoidable, as the lack of gravity weakens muscle strength. The cardiovascular system readjusts, potentially leading to decreased heart function and blood pressure regulation issues. Immune suppression and visual impairment are also common. To solve this, the ideal solution is artificial gravity created by rotating the spacecraft to simulate centrifugal force, though this requires massive structures. Currently, high-intensity exercise using space treadmills and resistance equipment is essential, alongside supplements like calcium and vitamin D. In the future, gene editing and regenerative medicine might provide more thorough solutions to help the body adapt to weightlessness. The long journey also brings immense psychological challenges. Astronauts live in confined spaces with a few companions, far from home, facing the solitude of the void. This can lead to claustrophobia, depression, and interpersonal tension. Rigorous selection based on psychological resilience is the foundation of mission success. During flight, support systems including remote counseling and virtual reality simulations of Earth's environment will be vital. Habitats must be designed to simulate natural light and provide private areas to relieve the pressure of confinement. For journeys lasting centuries, the concept of a generation ship emerges, where multiple generations live and die within the craft, with only the descendants reaching the destination. This brings complex social and ethical challenges. Another solution is hibernation or suspended animation, reducing metabolism to slow aging. While in early research stages, reversible hibernation would simplify life support systems and shorten the subjective travel time for the crew. Ensuring a long-term crewed mission requires a closed-loop life support system that recycles water, air, and food. Efficient wastewater treatment and urine recovery are essential to reuse limited water resources. Air systems must remove carbon dioxide and regenerate oxygen, perhaps using the photosynthesis of algae or plants to mimic Earth's ecosystem. Food production is an even greater challenge. Space agriculture using hydroponics, aeroponics, or vertical farms will be necessary to provide fresh nutrients. Waste management, including recycling and safe incineration, is also required. Managing the energy of such a complex micro-ecosystem is a massive task, likely relying on nuclear energy or giant solar arrays. Ultimately, humans may need gene editing to enhance radiation resistance and improve bone performance, moving toward becoming a true interstellar species. The driving force of interstellar flight is not just curiosity but the search for new homes and resources. The exploration of exoplanets, especially habitable worlds with liquid water, is a primary goal. Astronomers use techniques like the transit method, radial velocity, and direct imaging to find these distant worlds. Once discovered, we study whether they lie within the habitable zone. Famous candidates include Proxima Centauri b and the planets of the TRAPPIST-1 system. We also look for biosignatures, molecules like oxygen or methane in the atmosphere that suggest life. Beyond finding homes, asteroid mining offers huge economic potential. These are not just rocks but treasure troves of iron, nickel, cobalt, and rare earth elements. Many also contain water ice, which can be broken down into hydrogen and oxygen for fuel and life support. To harvest these, we are developing robotic mining, three-dimensional printing in space, and in situ resource utilization. This could alleviate resource depletion on Earth, though it raises legal questions about ownership. The Moon and Mars are our first stepping stones. A lunar base serves as a training ground and a jumping-off point, where lunar soil can be used to extract oxygen or build structures via three-dimensional printing. Mars colonization is a grander goal, aiming to establish a second home for humanity. Data from rovers has confirmed the past existence of water, making it a prime candidate for finding life. Terraforming Mars to increase atmospheric pressure and temperature is a long-term vision, though it sparks ethical debates about our right to alter another planet. Other targets include Europa and Enceladus, which likely have subsurface liquid oceans that could harbor life. Titan, with its thick atmosphere and methane lakes, offers a unique environment for exploration. Interstellar flight will trigger a technological explosion, with spillover effects benefiting all of humanity. We will develop ultra-strong, radiation-resistant materials and revolutionary energy sources like fusion that could provide clean, limitless power on Earth. Artificial intelligence and robotics will reach new heights, while life sciences will find new treatments for diseases through space-related research. Communication will leap forward with laser and quantum networks. Furthermore, this journey will trigger deep philosophical shifts. Finding even simple extraterrestrial life would overturn the idea that we are unique, impacting our religions and values. As we colonize space, we may even evolve into new species or merge with machines, raising the question of what it means to be human. Space exploration also serves as the ultimate insurance for our civilization. If Earth faces a catastrophe, humans living on other worlds could ensure our survival. Looking at the roadmap from science fiction to reality, the next century will focus on permanent bases on the Moon and Mars and the start of asteroid mining. In the medium term, 200 years from now, Mars travel will become routine, and laser sail probes may reach Proxima Centauri. In the distant future, centuries away, we may build a true interstellar civilization, expanding to other star systems and perhaps forming an interstellar federation. If faster-than-light travel is ever proven possible, it will be our greatest breakthrough. The sea of stars is calling. Interstellar flight represents our curiosity, our challenge to limits, and our desire for a future. It requires the wisdom of scientists, the skill of engineers, and the courage of explorers. Though the road is long and filled with uncertainty, this pursuit defines the glory of human civilization. Every time we look up, we feel the call of the cosmos. In the near future, through our collective intelligence, we will break the bonds of Earth and set sail for the stars, opening a new chapter for humanity. That is all for today's sharing. I wish you all a wonderful dream and a beautiful day. See you next time.